Hey everyone, and welcome. Today, we're going to dive into one of the most fundamental processes in the entire universe, radioactive decay. It's the invisible engine that powers stars, helps us date ancient artifacts, and even saves lives. So let's get right into it and unlock the secrets hiding in the atom's core.
All right, let me start with a question for you. What on earth could possibly connect the smoke detector on your ceiling, the way we figure out how old dinosaur bones are, and some of the most advanced cancer treatments we have? Well, the answer, and this might surprise you, is the exact same microscopic process. And trust me, by the end of this, you're going to see exactly how it all connects.
Okay, so it all starts deep inside the atom, in its incredibly dense core, the nucleus. You've got to picture the nucleus as this place of just insane tension. It's a constant battleground where these immensely powerful forces are locked in a super delicate dance.
So you've got these two major forces duking it out. On one side, you've got the strong nuclear force. Think of it like the universe's strongest superglue, holding all the protons and neutrons together, but it only works when things are really close. And then fighting against it is the electrostatic force. You know, all those positive protons, they hate being next to each other and are constantly trying to fly apart.
So, what happens when that balance gets thrown off? Maybe there are too many protons, or the whole nucleus is just too bulky. Well, it becomes unstable. It's buzzing with too much energy and it desperately needs to chill out. And nature's solution? It's actually pretty elegant. It's called radioactive decay. It's how the atom gets back to a stable state, basically by just jettisoning some energy and particles.
Okay, so how does an atom actually do this? How does it rebalance itself? Well, the first way is to just get rid of some serious weight. We call this one the heavyweight champion, alpha decay.
So what is an alpha particle? It's just a little bundle of two protons and two neutrons, all stuck together. And if that sounds familiar, it should. It's basically the nucleus of a helium atom. The unstable atom is literally just spitting out a piece of its own core.
And this is a real transformation. You have the unstable parent nucleus, it chucks out that alpha particle, and because it lost two protons, its whole identity changes. I mean, it is no longer the same element. It's become a brand new, slightly lighter daughter nucleus.
Now, alpha particles, they've got a real personality. They're big, they're bulky, and that means they have a ton of ionizing power. Think of them like a bowling ball crashing through pins. They can do a lot of damage to any atoms they slam into. But that same size also means they have really low penetrating power. Seriously, a single sheet of paper or even the top layer of your skin can stop them dead in their tracks, and that is exactly how a tiny bit of an element called americium-241 can sit inside your smoke detector and be totally safe.
All right, next up we've got beta decay. And I like to call this one the transformer because it does something amazing. It's like subatomic alchemy. It changes an atom's identity from the inside out.
So instead of spitting out a chunk of itself like in alpha decay, here the change happens right inside the nucleus. What happens is a neutron just turns into a proton. And when it does that, it shoots out this super high energy electron. That electron is what we call a beta particle.
So let's walk through that again. You've got your unstable nucleus, a neutron inside it flips and becomes a proton. The total number of particles, the mass, is still the same, right? But the number of protons just went up by 1. And since the number of protons is what defines an element, boom, it's literally transformed into the next element on the periodic table.
So, beta particles are kind of the middle of the road option. They're way smaller and faster than alpha particles, so they don't cause as much damage when they hit something. But they can get through more stuff. They'll zip right through paper, but a thin sheet of aluminum will stop them. And this right here, this is the engine behind radiocarbon dating. It's the decay of carbon-14 that lets us figure out how old ancient bones or artifacts are.
Okay, and for our final type, we've got something completely different. This one isn't about changing particles at all. Gamma decay is just a pure burst of raw energy. You can almost think of it as the nucleus just taking a deep breath and letting out a sigh of relief after all the excitement.
So here's what's going on. A lot of times after an alpha or beta decay happens, the new nucleus is left all jittery. It's in a super high energy, excited state. It's still got way too much energy, and to finally calm down, it releases that extra energy as a gamma ray, which is just an incredibly high energy photon, a particle of light.
Now, the important thing here is that nothing really changes. The number of protons and neutrons stays exactly the same. The element is still the same element.
All that's happening is the nucleus is going from that hyper-excited state down to its stable, calm, ground state. Yeah, it's kind of like a bell that's been struck. It rings loudly, and then it just fades into silence.
Gamma rays are wild. They have no mass, no charge. That means they have very low ionizing power, but that's also what gives them their superpower. Insane penetrating power. They'll go right through paper, aluminum, even you. You need thick sheets of lead or solid concrete to have a chance at stopping them. And it's this exact ability to penetrate deep inside things that we use in radiotherapy to target and destroy cancer cells without ever having to cut someone open.
All right, so that's the big three, alpha, beta, and gamma. Now let's kind of put it all together and talk about how we actually measure and use this incredible power.
This chart really lays it all out, doesn't it? You've got alpha, the big slowpoke. It's a heavy hitter, but easy to block. Then you've got beta, the zippy little electron, right in the middle in terms of power and penetration. And then there's gamma, no mass, no charge, moving at the speed of light, and can get through almost anything. They each have their own very distinct profile.
Okay, but how do we keep track of how fast this stuff decays? Well, the key concept here is something called half-life. Think of it as the universe's most perfect, most reliable clock. It's simply the time it takes for exactly half of a group of radioactive atoms to, well, decay. And this can be anything from a tiny fraction of a second to billions and billions of years. And just to give you a sense of that scale, get this. The half-life of uranium-238 is 4.5 billion years. And that's not a coincidence. That's pretty much the age of planet Earth. And it's exactly how scientists figured that out, by using these atomic clocks.
Now, obviously, with all this power comes a pretty big need for safety. But the rules for staying safe are actually pretty simple when you break them down. It all comes down to three things: time, distance, and shielding. Less time near it, more distance from it, and the right kind of shield between you and it.
And that, brings us full circle right back to that question I asked at the beginning. Smoke detectors, carbon dating, cancer therapy, but also medical diagnostics, nuclear power plants, tracking pollution, sterilizing medical gear. The list goes on and on. This predictable, powerful process has become an absolutely essential tool for pretty much all of modern life.
So this whole process, this transformation that's born out of instability, it's not just some weird physics thing. It's given us this incredible window into the past of our universe and some seriously powerful tools to build our future. And it really makes you wonder, right? As we get even better at understanding and controlling this atomic power, what other huge mysteries are we going to solve next?